Hello everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at EasyPower. The primary purpose of this series is to cover a bit more depth on specific aspects of the EasyPower tools and some of the features that may not be covered as often as they need to be in normal day-to-day use. Today we'll be talking about stuff that you may be missing if you're not using EasyPower's Power Flow. This is one of those topics that you can be exposed to multiple times, but until you actually run into the situation that requires that feature, it may not really sink in. I speak from firsthand experience. So as we're in the habit of doing, we'd like to start with a poll question. Appreciate everyone attending today. And if you would please respond with your position on how recently have you or your facility completed a power flow analysis. No liability or obligation, strictly just trying to get a feel for your perspective or the general perspective on the topic. We'll leave this open for about another 5 seconds. Looks like we have a quorum. Here's how people have responded. I'm impressed that 25% of the folks have done a power flow in the last month, which I applaud. Excellent. And then the second question is, in your opinion, how often should a power flow study be completed on a typical industrial facility? Again, it's not a right or wrong answer. It's strictly your opinion or your perspective. And in some regards, I kind of think it reflects the current state of facility controls, frankly. So let's leave this for another 10 seconds. Looks like we are close to a quorum. So here's how folks have weighed in. Looks like the heavy favorite is once a year, which is not necessarily good or bad. It's just good opinion. Okay, so let's jump into the world according to Jim Chastain. So power flow basically gives us the ability to produce instantaneously results for three-phase AC and DC systems. And these include the actual watt and var flow, the voltage drop at each bus, the losses and overloads, and then take on some what-if scenarios if we want to either optimize or move capacity around in our system. I'm not going to go through all the details of how power flow does this. What I'm going to do, what I'm going to spend the next 30 or 40 minutes on, is basically 5 common tasks. First, we're going to do some scaling and see what reference we use to start the process. Then we're going to use EasyPower to do an accuracy check on our one-line diagram, do some optimization by verifying the tap settings or calculating what the optimized tap settings on a transformer might be, identify potential sensitive elements for motor starts, and then investigate options to improve power factor. Interestingly enough, just recently I heard an industry pundit make the statement, it's ironic that we spend lots of time analyzing for an event that may never happen, specifically a three-phase bolted fault, and little time analyzing everyday operations. I just thought that was interesting. Well, no model is perfect. And so there's always room for improvement, not to cast aspersions on weather forecasting, but now that we're getting into hurricane season, generally we see anywhere from 8 to 10 different plots for hurricane paths. So no model is perfect. In EasyPower, the typical arc flash 1 line is based on the NEC guidelines for capacity. And usually that's a max load demand with some percentage guard band. And so one of the ways to improve the database is to match the loads with the real-time meter readings or peak data from the utility bill, and then scale loads to match those numbers that we've read or have from a independent source. Now, just forewarning, it's recommended that as you're doing data collection for an arc flash study, if you have access or if the equipment has metering systems, it's not a bad idea to write down or make notes of the volts, current, and VARs from the meters as you collect the data, whether an arc flash study includes doing the power flow study or not. So more on that later. So when we're scaling loads, the good place to start, or the best place to start, is with the utility bill, because these are the people that stake a fair amount of importance on the accuracy of the power that's being supplied to any particular customer. And then utilize the equipment metering as it becomes available. This includes stationary metering or portable metering. And the farther downstream the readings are made, it will increase the accuracy of our model. So in scaling EasyPower, there's basically three options. Individual loads can be scaled. We can scale a group or in mass elements in the system, and we can import SCADA results. So we're going to touch on each of these. So let's start with a typical system. Paul's got a question already that he had a convergence problem on the power flow being unstable. Yeah, I can talk a little bit about that as we get into this. I didn't include any examples of that, but that's actually one of the more fun exercises, in my opinion, is to understand where your convergence issues are coming from. Okay, so let me go into EasyPower. Here's a one-line system that has a fair amount of detail in it. And I want to look at just one typical load. For instance, this particular motor, if we open up the dialog box in Database Edit and we look at the Power Flow tab, we can see that it's based on the load model, which is the motor specification, and it's scaled for 100%. So this is the default setting when we're building the one-line diagram for any motor that we place in our system. So as a result, the total loading on the system, and there's error warnings in EasyPower as we make adjustments or we build a one-line. And what I'm going for as a result of all this are errors that may be propagated in spite of the warnings that are in EasyPower. And I think Paul has one coming up. All right, so I'm going to go back to my whole system. Actually, I'm going to go to the utility focus and solve the power flow equations. And we see with the way things stand, we have, so this on the top of the line, or the unparaphrased value, this is the VAR, the real kilowatts, or in this case, megawatts. And in parentheses, we have the VAR flow. So this number is the result of 100% loads at every point in our one line. Well, it turns out in our utility system, our utility monthly statement, we see a typical value, an average value of 13.1 megawatts and a peak of 9.4 megavars, which is where the maximum setting of our system ought to be for power flow. So we're going to go to the whole system and scale, see if we can't match that, something close to that number. So I'm going to select the whole system, go to scaling. Let's start off with our constant MVA loads at 65%. And we have a belief that our motor loads run about 70%. So let's see what that does for us. So we're going to scale all of these at one time. Let's go back and look at the utility calculations. So now we see with that scaling, we have an 11.46 megawatts and 8.56 megavar, which is considerably closer to the real value that we're seeing. Now let's say we know that we've got a reading on a bank of 2400 volt motors, which is right here. And so we're going to scale all of these to 85% because we know that to be the case. So select these, scale, make this 85%. And then we know an individual motor MT53. So let's go find that. And we have a reading on it for 50%. So if I scale this individual motor for 50%, I can go back and look at my utility results. And now with just those 3 data points, we have something that is not that far off from our actual peak value according to utility company. Now, anytime I want to check the results in power flow, I have the ability to calculate a number of reports. For instance, right now I want a voltage drop report, and while we're at it, let's look at a voltage violation report. And by requesting those, they instantly show up in my list of windows. And so I can see I have fairly good matching for my majority of my buses, a couple that are out of whack, or at least out of that 10% guard band that I've set. Now, we also have the option of utilizing SCADA data or importing SCADA information to do the scaling. So let's I'm going to simplify this just so you can see how it works. But right now we're going to pick out a single motor load in a more simplified one line and show the process of doing SCADA importing. Let's not save this. Go ahead and close out of this. All right, so the motor that we're talking about is M4. And again, when it was set up originally in the one line, it was set up scaled to 100%. Now we have SCADA information that we can utilize to scale the actual value that this is running at. To do that, though, or to make the input, I need to align with the SCADA report format within EasyPower. So I'm going to export first from EasyPower SCADA database. So under export a database, I'm going to give it an original name so I can find it. And it's in this folder. Now it's not just a typical CSV file, it's a SCADA CSV file. So you don't want to use Excel to open it up. By generating that report, now I can go out and look at it. Here's the report I just generated. And now rather than using Excel, I'm going to pick it up with a text editor. In my case, it's Notepad++. And so you can see all of my data comes in this particular format. Now, what I'm looking at is M4, the orientation of the spec data and then the SCADA data tells the computer or tells the program which one to utilize. And because SCADA is second, the spec is is being utilized by the program. So I want to advance the SCADA information. To do that, let's say we're running at 950 kilowatts and 450 kVA. And now rather than delete the spec data, I'm just going to comment it out. So we're going to go into my text editor, put a comment, colon, and I'm going to save this. Just for efficiency's sake, I'm going to save the same name, the same location. So let's go back to my EasyPower. Now I'm going to re-import that same information with the only change being M4. So I'm going to import SCADA, use that file that I've been playing with. Now when I go back to look at this, the data dialog box for this motor power flow tab, you can see now it's using the SCADA information, and it's utilizing the data that was read off the SCADA metering, and I still have the ability to scale it if I need to do so, or if I want to do so on a what-if scenario. So that's the three methods: individual scaling, group scaling, and then SCADA import. Next, we want to use the power flow to do some error checking in our one-line diagram as it stands. So I'm going to go back to that original one line I used or had. Get rid of this guy. Okay, I want to look at T5. Now when I've run power flow with this current scaling, I can see that, just kind of picking out one example, this cable is showing that it's overloaded. By virtue of these two icons here on the top, I can show voltage violations and then overload violations. So this cable is overloaded. If I look at the marking or the parameters, it's designed, or the ampacity is 250 amps, and right now it's being exposed to 471 with a 100% motor. Well, even if this thing was 50%, I'd just barely be inside. I'd be inside the ampacity for that particular motor. So it's obvious that I have a problem with this cable. And the first thing I want to do is go back and look at the notes that I took in database edit. And sure enough, my notes say there's 2 conductors per phase, and I only drew the one line with 1. So I'm going to put in 2 conductors per phase. Now, because this model was made with an old version of EasyPower that didn't auto-calculate, I want to make sure that I do auto-calculate, which brings up my ampacity calculation. And now when I go back and analyze power flow, I show a 510 amp ampacity, and at 100%, it's red only because it's within my 10% threshold. Now, that's all well and good, but let's see what else is going on. On this transformer, I'm seeing that it's rated for 1549, but right now it's trying to push out over 2 megawatts, or 2 mega amps. And so it's again occasion to go back and check my notes. I go in and see what's recorded for this transformer. Sure enough, it's rated for 1500 kVA, and I had it improperly set it up for 1000. So let's make that adjustment. And then go back and see what that does to my error reports. Okay, so now it's rated maximum for 2323. It's flagged red because I'm within that 10% range, but at least now it's not being over-dutied or over the threshold. Brings up another question. Why is all this demand being pulled, and why is this bus giving me an error for voltage violations? Well, and so that might be an indication of the need for power factor to raise the voltage, a capacitor on the bus. But more importantly, what have we set up for taps on this particular transformer? So let's go back to the database and check this out. When I look at the setup, I don't have it tapped for anything. My choices are I can go back and adjust the tap manually in PowerFlow, or I can have PowerFlow recommend the optimum settings. It may be that I couldn't see the taps when I did the data collection, so I'm going to use EasyPower to optimize what those taps ought to be. So even though there's not a load tap changer in this device, I'm going to pretend there is one. We're going to adjust the tap on the from side to hold the voltage on the to side. And we're going to optimize by running PowerFlow, and it will find a quiescent point that gives me, holds a 480 volt output. So now I'm looking at a good voltage control or voltage base if I tap this transformer at 13.58. So instead of having 13.8, let's put 13.58. And oh, I did that wrong. Did you guys catch where I made a mistake? It's going to do this again. Okay. Yep, 13.058. Sorry about that. So okay, so now we get the proper results. Okay, so that makes everybody happy. I'm not overloaded on my cable. I don't have a voltage violation. I just need to make sure my tap settings are at this recommended value. That was more fun than I tried to make it. Okay, so that's a case. Now, a point to be made here is that even if the customer or the client hasn't asked for a power flow study, by being able to do an error check on my one line actually corrects mistakes I could make in short circuit analysis. And it's hard to say whether the result would be a more conservative arc flash result or not, but the fact is I will have a more accurate one-line diagram as a result. Okay, finally I want to look at some motor start issues. Built into EasyPower PowerFlow is a feature called Impact Motor Start. And if we look at T7 in my one line, this is my 2400 volt series. You might expect some issues with starting any one of these large motors. So here's a 2000 horsepower Let's go back to the database. So we have 2,500 horsepower, 1,200, 1,750. So the question is, where's the sensitivity? If I start one of these motors, how does it affect the rest of my system? So I go back to power flow, and again, these are all set for 100%. So take that into account. And when we do solve, we're optimizing, or we're looking for a quiescent point where everything is stable. If I go in and set up this particular motor to be offline initially and then give me the ability to start it, what it's going to produce is the instantaneous results when a motor with a locked rotor is put across the line. So if I solve it, again, we see this motor is not running yet. If I solve it, I can see I have an effect on these buses, this bus downstream, and obviously this cable upstream for some period of time. Likewise, is it worse if and as I would expect, is it worse if I start two of these motors at the same time? So I can do that just by setting the other motor up, offline, solve, and then start the motors. And sure enough, we do have the potential for sensitivity at remote buses, at least, and depends how critical those loads are or the control systems that are on them. And we may want to have a staggered start requirement or soft starts with different time settings if we're bringing up these motors. Now, let me just touch on power factor, and then we'll get back to a couple of the questions. So power factor sometimes can be an expensive proposition. And if we go back to our SCADA protection, which is a little more simplified and easier to discuss, we'd expect these large motors to have an impact on power factor. Well, even though we're in power flow and we solve the equations, we're not seeing any overloads, but we're seeing a large amount of reactive power flow, especially through this leg. Is there anything bad about that? Well, because this is going to be flowing through all the system from the utility to this point, there's individual losses, or there's losses as a result. And we can see what those are by using this icon here, and we see it's not above a certain threshold. So these are in megawatts and megavars, and the losses are in kilowatts and kilovars. So it's relatively small compared to what the load is actually demanding. But the real issue ends up being what's going on with power factor. So if we come in here to our power flow options, and on our one-line output, look at the generator and loads in MVA power factor, we can see we have a power factor of 0.8, which, at least in this part of the world, would invoke a power factor demand penalty, and it could be substantial for an extended period of time. So the question is, what are our options to deal with that? Well, we can go through some what ifs. First of all, we have to deal with 1.65 megavar of flow. If we go back to our database, one option is to put in a power factor correction capacitor. Let's put in a switch just to play with it. And let's set it for just slightly less than the total value, 1.55 megavars. What does that do to our result? So we put 1.5, and we put in 1.55, and we're getting 1.52. Part of that is because we have a higher voltage, but we've reduced the flow through the circuit by over a mega bar, which is impressive. So our losses will be diminished quite a bit. But what's more impressive is that by putting that power factor correction in, we bring our power factor correction up to a sterling 0.97, which gives us well within the issue working with the utility company. But there's trade-offs in doing that. One is cost. Another is what happens when these motors are offline individually and the capacitor is still in line. And what we can see when these two motors are offline and the capacitor is still on board, that we have real power is reduced, reactive power is actually going the other way, so we're in a capacitive mode, and we're no longer leading, and we're missing the boat with utility demand factor, again outside the range of power factor. Another alternative while we're doing this is saying, well, another way to deal with this is to make these motors VFDs. So let's see what happens there. Let's just make two of these motors VFDs. Again, there's a trade-off involved. We'll deal with that shortly. Doesn't really change anything short circuit wise, but it will change things radically in power flow. So let's make this a adjustable frequency drive. And let's go back to power flow. Let's bring these online. Let's take out the capacitor. Now we've reduced the power flow. We've reduced the reactive power flow. And if we go back to we don't have quite as good power factor, but it's much better than when we had with the real inductive motors. Now that doesn't mean that the best answer is VFD drives, because they induce resonance harmonic issues, and that's just the beginning of the story. So let's not get too carried away with the solution. The point I'm trying to make, it gives me a nice what if, and I can cost out the different options just as a order of magnitude based upon what the trade-offs involve. So Pram is asking, when the scaling was done on the completed system to 80%, why did the medium motor still at 100%? When I close the file, or if I go back to database edit without saving the adjustments that I made, in other words, I made some adjustments in power flow. If I go back to database edit, it's going to ask me if I want to save temporary settings. If I say yes, then it'll save those adjustments. If I say no, it takes me back to what I started with. So that was a little bit of a bait and switch there. Sorry about that. Now, Paul's question about the convergence being unstable. As far as I'm concerned, this is one of the most fun aspects of power flow, and it does uncover the potential for mistakes in the one line in sizing different elements. And the answer is, or the suggestion is, treat it like a detective story. If I go into power flow and I try to solve my equations and I get an error that says it doesn't converge, what I do is I open up all of my feeder breakers. It's nice to start up on the switch gear or the main, take them all off, solve. It should give me the results. Obviously there's no load, but at least it shows me some results. And then one at a time, put it online until it crashes again. And the last one that I put online, that's where my error is. And you work your way down to any feeder system and locate the problem. If you don't find it Be happy to help you out. If you want to send me a copy of your DZ file, or if you want to talk to tech support, it's another way to kind of deal with it. Okay, so what have we done? We basically showed multiple ways to do scaling the loads, which will improve the accuracy of our power flow calculations. We can do an error check on the accuracy of the one line itself without even doing a full power flow study. We can get optimum tap settings by pretending we have a load tap changer and seeing what the tool optimizes on for taps. We can identify potential sensitive elements during impact motor start. And then we have the ability to do what ifs on capacity changes and adjustment. Yeah, Roland is saying most of the time when he sees a convergence issue, it's because he's typing in megawatts when he meant to use kilowatts. And that's a good point. All right. Appreciate everyone attending today. My recommendation is to consider the time invested in an ArcFlash database as an investment and utilize PowerFlow to capitalize on the optimization of that system to get a return on your investment. Be sure to check the website for tutorials, examples. We have live training set for later in the year. And if you've got questions, be sure to contact tech support at easypower.com. Just as a real quick reference, we have a two-part series on PowerFlow, 1-hour webinars that are an excellent resource for a full-blown explanation of PowerFlow that get into a lot more detail. I highly recommend anyone utilizing these as a reference if you're using PowerFlow. Thank you for attending today. I'll hold open the question line for the next couple minutes. Have a good day.